So this is part of joint work with Nima Arkhani, Hamed, Hadley Frost, Pierre Plamondon, and Giulio Salvatore. And you might recognize one of those names. The other three are physicists. And I'm going to be talking about the representation theoretic end of the project, but there is a real physical motivation in string theory, which I'll get to at the end, though I'll be kind of brief necessarily. So we're going to begin with just some quick reminders about tau tilting theory. We have finite dimensional algebra over a field n isoclasses of simple modules, and then the key role is played by the compatibility degree of two modules. So this is, by definition, the dimension of the Hom space from m to tau n plus the dimension of the Hom space from n to tau m. And we're going to be particularly interested in tau rigid modules. These are the modules that are compatible with themselves. And then it turns out there's a simplicial complex structure whose vertices are given by these indecomposable tau rigid modules together with these funny n extra guys. And if you've seen cluster theory or various places, you may have some feeling about why there might be n extra guys. And you might have some feeling about why I would notate them like this, but you don't really have to worry about it. There's just some n extra guys who are also there naturally sort of filling in the picture, filling out the simplicial complex. And so in order for, so I need to define compatibility degrees for them as well, which we can do like this. And then the faces of the simplicial complex, this tau tilting complex, are just the mutually compatible subsets. And it turns out that the maximal faces all contain n vertices where n was the number of simples to begin with. Okay, so this is this tau tilting theory introduced by Adachi Uyama some years ago now. Okay, and let's just take a quick look at A2 just to make sure we're on the same page. So in this case, we have 3 indecomposable modules and 2 shifted projectives. And the simplicial complex that we get is just a pentagon. The maximal faces consist of pairs of vertices, which are mutually compatible. So like the projectives are compatible because we check that Hom x tau y and Hom y tau x are 0 if you started with 2 projectives, for example, because the taus of the projectives are 0. So that's just going to work very well. But you can check that this is the simplicial complex that you get for A2. So now, really the point of my talk is I'm going to introduce, and so I'm sort of advertising a definition. And I think it's a definition that's really interesting. I think there's a lot to be discovered about it, which remains really to be worked out largely. And so this definition are what we're calling the U equations. And this is going to be some variant. It's going to turn out to be closely related to tau tilting theory. So we're going to start off with the collection of all the isomorphism classes of indecomposable modules, so including the non-tau rigid ones. We don't put in tau rigidity as any kind of input. We have these. We have this collection of all the indecomposable modules and the shifted projectives again. And then I'm going to introduce a variable for each of these elements of this index set I. And I'm going to introduce an equation, one equation for each variable. And this is the equation. So we just take, so for each m in the index set, for each indecomposable module or shifted projective, we take um plus the product over everybody in the index set of its compatibility degree with m. And then the sum of these two terms is supposed to be 1. And then we're going to look at the affine variety cut out by these equations over the complex numbers. And we can ask ourselves what, well, I mean, of course, we can write down a bunch of random equations and, so I'd better try to convince you that there's something interesting to say about them. So first of all, I want to explain in a, quickly how these equations sort of capture tau tilting theory. So if I have a maximal simplex in the tau tilting complex, so this is a maximal collection of n modules or shifted projectives that are mutually compatible, then that determines a particular point in the variety cut out by these equations. I can set the UNI to be 0 and everybody else to be 1, and that will work. And it's because you just think about what's happening in this equation. If we look at the equation for some ni, then this term is 0, but this term is 1. And if we look at the equation for somebody that's not an ni, then this term will be 1, but this term will turn out to be 0. So everything's satisfied, and somehow this just, and if you sort of think about it, you kind of you sort of realize, oh, okay, this just seems like I've just kind of built something that just has the same combinatorics. If you think about it only putting in zeros and ones for the u's, you just see that you're getting the same combinatorics out as the tau tilting combinatorics. And I wrote out the A2 example. What you see, there are these 5 points that are the 5 points that I mentioned before. And what you find is that the region where everybody is positive is actually kind of this pentagonal shaped thing sitting, but curvily sitting inside C5. Okay. So the thing that I think makes this a bit exciting is that we can actually write down an n-dimensional family of solutions to the U equations, and we conjecture that fully describes the solutions. That describes all of them. We can't prove that yet. So to do that, I need to use F polynomials. F polynomials are an important invariant of a module, which were introduced in the setting of cluster algebras. But if you're not familiar with them, you don't really have to worry about the contents of the slide here. The point is just that to each module, there's an associated polynomial in n variables, which somehow encodes the structure of the submodules. And again, it's not so important to the detail of what's in the theorem is not so important, but what it's saying is that there's a way to solve all the U equations. So there's a way to solve the U equations in terms of as rational functions in the y's. And so you can put in values for the y's and you get this n-dimensional family of solutions. So you get this, yeah. And so the proof of this uses a result of Dominguez and Geis, which is an analog of the mutation formula for F polynomials, but it works for any finite dimensional algebra. And so we kind of feel like this is like part of cluster algebra theory, but that works for any finite dimensional algebra. And in particular, if you started with a Dinkin-Quiver, then what you're getting is really something that's very close to the solutions to the U equations are very close to a subset of the Fock-Goncharov X variables, cluster X variables, but you can do it for any finite dimensional algebra. I should have emphasized, it was on the slide, but I don't think I said it. I should have emphasized the way that I presented it now is only working if you have, if you're in finite representation type, because we had to have this finite set of modules. So, but it's very interesting to extend it to non-finite settings. In particular for this motivation, which I'm going to just say a word about before I end, which was that this story of these equations were written down in 1969, and the region for the AN case, and it turns out that the region where all the U's are positive is the region which you need to use to integrate over to get the so-called tree string amplitude. And So replacing an by other gentle algebras that correspond to triangulations of other surfaces, you can use that to define other integrals, which will provide higher loop corrections. So this is something that the physicists were really motivated by, and well, that is sort of where this project starts. Anyway, I'm out of time, so I should stop.